Good morning, afternoon, evening. How y'all doing today? Welcome back to Mr. Moore's Algebra 2 class. Today we're going to talk about radicals, guys. In specific, we're going to talk about nth root radicals and rational exponents. Radicals sometimes are confused for square roots, and I want to get rid of that misnomer immediately right now. A square root is a square root. It is a particular type of what's called radical. Okay? A square root is this. Square root of 4 equals 2. Square root of 16 equals 4. Square root of 50, that's 25 times 2, so that's 5 square root of 2. A square root is a radical sign that has no number here. Okay? No number here. There's an invisible number there, really, and it's a 2. And what the square root tells you is it says to the reader, hey, do that. What number times itself gives you the value inside of this radical? And that's why the square root of 4 is 2, because this breaks down to a 2 and a 2. Bless you. So there's 2 2's, and it comes out as a 2. 16. This is 4 times 4, so there's 2 2's and it comes out as a 2 4's and it comes out as a 4. How did this square root of 50 work out? Well, this is 25 times 2. 25 is 5 times 5. A 5 and a 5 comes out as a 5, and I have a leftover square root of 2. Everyone here in this class should know very well how to simplify a radical. We've worked with them already with the square roots as well, completing the square, quadratic functions. So that's a square root, okay? Square root. Today, I want to start talking to you about nth root, because you can have radicals with different roots, and they're called nth roots. Let's look at it this way. If a to the n power equals b, with a and b as real numbers, and n is a positive integer, then a is the nth root of b. What am I saying? Let's look at 2 to the third. 2 to the third equals 8. If I take the cube root of 8, what I'm asking again is the same question that I asked for a square root, but this time I have a cube root. So I'm asking the question, what number times itself 3 times gives me the value inside of this radical? And that would be 2, because 2 times 2 is 4, times a third 2 is 8. So the cube root of 8 would be 2. Okay? So anytime that you have a radical, you're going to look at what's called the index. Right? When you have a radical, this guy right here is called the index. All right? This is called the radical sign. And the value inside is called the radicand. All of that is old knowledge. If you know that, it's going to make life a lot easier to work with things. So now, there's a situation with these indexes. If the index n is odd, that means 3, 5, 7, if it's odd, there is one real nth root of b, denoted in the radical form as nth root of b. If I have cube root of 8, that's 2. If I have the cube root of negative 64, that's negative 4. If I have the cube root of 125, that's 5. Cube roots can be negative, as you can see, because a cube root relates to a number being multiplied times itself 3 times. So if I have, for example, this guy right here, the cube root of negative 64. Cube root of 64 is negative 64 is the is negative 4 because negative 4 times negative 4 is 16. Times a negative 4 is negative 64. So I can, yes, have negative radicands inside of odd indexed radicals. You with me? However, excuse me, if n is even, it's a whole different ball of wax. When b is positive, okay, inside of an even root, there are two real nth roots. We know this. There's a plus or minus. There's a principal root, which is positive, and its symbol is just the nth root of b. The negative root is its opposite, or the negative nth root of b. When b is negative, there are no real even roots. When b is negative, there are only real roots for odd indexes. So odd indexes can have negative radicands. Even indexes cannot have negative radicands. You can use a radical sign to indicate a root. The number under the radical sign is a radicand, and the index gives you the degree of the root, which I already described, but it's nice and pretty here for you. You have to know this. If you do not know this, you cannot go forward with any type of word problems or description. They're going to ask you for patterns, and if you don't know the definitions, the words, the vocabulary, you will not know how to do this. Please remember that if there is no index, then it is a square root. That means that the index equals 2 when it is blank. Okay? So far we know what an index is, what a radical sign is, what the radicand is. We know that we can have negative values inside of any odd index. So we can have a negative radicand inside of any odd index. We cannot have negative values inside of an even index. What happens when we have a negative inside of a square root? We talked about this already. Exactly, it's I. It's an imaginary number. So you don't have any real roots when you have a square root of a negative number, but you do have imaginary roots. Now, if my index n is greater than or equal to 2, it's greater than or equal to 2, and even, the radicand, like I said, must be greater than or equal to 0 for you to have a real answer. If not, it will be an imaginary answer. If my index n is greater than or equal to 3 and odd, then the radicand can be any real number, positive or negative. I just don't want you to start pulling out i's from a fifth root, for example, because that would be totally inaccurate. The only time there's an I is in a square root. Okay, moral, but here it says if n is greater than or equal to 2. What if n is 25? Or I'm sorry, 26. That's even, Mr. Morrow. There's no I. There's just no solution. Okay? You can't have a negative inside of any even root. If you have a negative inside of a square root, you can pull out an I. But if not, it's just no solution. Yes, sir?
So for a cube root, if you had a cube root of 15, that wouldn't be a solution.
Cube root of 15, no, that would be as simplified as possible. Because what number times itself 3 times gives you 15? That's right. Good job. The answer is nothing. Okay, so let's move on. When you are finding real roots of a number, you use the index to determine how many values are needed to pull out one of that value. So for example, I want the cube root of 64. So that means that I want 3 of the same number to pull that out. And that is going to be 4. But let me explain to you how and why that works so you don't have any problems later. 64 breaks up into 8 times 8. 8 breaks up into 4 times 2, circle the prime. 4 breaks up into 2 times 2. This 8 over here also breaks up into 4 times 2, circle the prime. And the 4 breaks up into 2 times 2, circle the prime. Now, according to my index, I am looking for sets of 3 in this particular problem. So every set of 3, you pull one of those values out. So a 2, a 2, and a 2 comes out as a 2 times. A 2, a 2, and a 2 comes out as a 2, which equals 4. Now, some of you may be saying, yeah, but I knew that already. I knew that 4 times 4 times 4 is 64. Then great, God bless you. There's no worries, brothers. However, what happens if you don't? I don't want to take that for granted. I want to show you how to do it. So I want the real cube roots of all of these bad boys. And I did this with the decimal on purpose. Yes, sir. What would the cube root of that be? Yes, sir, my brother. Oh, I thought you, I'm sorry. Yes, sir.
So, the example you showed us right now, when the digit repeats that 3 times.
Okay, I never said a digit repeats. Repeating digit would imply that it's repeating. No, that's not at all what happened here. What we said here, thank you for your honesty, sir. You have an index. That index tells you how many values of one particular number you need to pull one out. So I had a 2, and a 2. That's 3 2's comes out as a 2. Then a 2, and a 2 comes out as a 2. And 2 times 2 is 4. Thank you, my brother. Because I don't like that repeating word because that kind of implies that it just keeps going. Exactly. When they appear in this case 3 times, you pull out one value. If it was a 5th root, you'd need 5 of the same number. If it was a 7th root, you need 7 of the same number. Fantastic. Thank you, son. Good job. No, thank you. Yes, sir. Very good. The real cube root here of 0.008 is 0.2, guys. Now, some of you may say, no, it has to be 0.02. No, think about multiplication of decimals. 0.2 times 0.2, okay, gives you 4, but you have 2 decimals, so 1, 2 to the left. So you have 0.04 times 0.2, that's 8, 0, but you have 3 decimals, 1, 2, 3. That's 0.08. So the trick here is whenever they give you a decimal like this inside of a radicand, look at the index. Look at the decimals. You know that the number of decimals you have is going to be equal to the number of times that you multiply that number times itself. So since I have 0.2 multiplied 3 times, that means that I have to move the decimal to the left 3 times. Hence, 2 times 2 times 2 is 8. But it's 0.2 times 0.2 times 0.2. So that 8 goes 1, 2, 3 to the left. It's just knowing old school decimals. Just wanted to show you that because that tends to mess up a lot of people. What's the cube root of negative 1,000? That should be pretty simple. Negative 10. Very good. And last but not least, what's the cube root of 1/27th? Yeah, because the cube root of 1 is 1, the cube root of 27 is 3. Very good, my brothers. Excellent. Okay. Yes, sir. Excuse me. Because what is 1 times 1 times 1? It's 1. Thank you, sir. Good question. Okay. What's the 4th root of 1? 1. 1 to any power is 1, guys. Okay. What's the four? Oh, this is wrong. Wait. This guy here. Wait, 1, 2, 3. No, 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 it's not. Why do I second guess myself? What's the fourth? Whoa. What is the fourth root of this bad boy? Yeah, you can't do it because it's negative in here. If it was a square root, then you could pull out an I. Okay? How about the fourth root of 1681st? Very good. The fourth root of 16 is 2 because 2 to the fourth power is 16. And the fourth root of 81 is 3 because 3 times 3 times 3 times 3 is 81. Okay, next. Cube root of 8. That's going to be 2. Very good. Again, why, Mr. Morrow? I'm not understanding why. Well, I'm going to break this down. 4 times 2, and then this is 2 times 2. So a 2, and a 2 comes out as a 2, and that's my answer. I had 3 2's, and it pulled out as a 2. Now, it would really benefit you if you guys really knew your multiplication tables backwards and forwards like I told you to do day 1 of this class. Remember that? I told you guys, hey guys, it's going to help you a lot. This is now where it's either going to help you or hurt you, knowing it or not knowing it. So please try to really, really know your multiplication tables. How about this bad boy? It's not 0.02. It's 0.2 because 0.2 times 0.2 is 0.04. We just went over that. What's the fourth root of negative 1? Yeah, no real solutions here. Can't do that. What about, I like this. What about the square root of negative 2 squared? It's negative 2 because this square root cancels out with this 2, and it equals negative 2. Now you may say, whoa, Mario, you just finished saying that you cannot have a square root of a negative number. Yeah, I didn't. I can't have this. No, you're right. That's no solution. But I didn't have that. I had the square root of negative 2 squared. And everything was in parentheses. So that negative 2 is being affected by that power of 2. And we already learned that a square root cancels out a power of 2. Yes, sir. No, absolutely not. If it was like this, my brother, yes, it'd be I square root of 2 for sure. But this is negative 2 squared. Hold on. No, there's no I here, guys. No. Yes, this would be I square root of 2. Yes. Because there's a square here, son. This is different than this. So where are you confused? Okay. And go ahead, my man. Exactly. Whenever you have a square inside of a square root, you cancel, and it's just negative 2. That's it. Sir. Of course. All right. I had a very good question here, and I would like to address it. Being that we just canceled out a power of 2 with a radical, one of my students just finished asking, Mr. Morrow, then why is it that when we're using the quadratic formula, we don't just cancel out the radical? There's a square there. It's quite good question. You have the negative b plus or minus square root of b squared minus 4ac over 2a. The question, which again was very valid, very good. Morrow, why don't I just go bye-bye and bye-bye? Because the b is squared, but what about this subtraction? Is that being squared as well too? No, you can't do that. You can't break up individual binomials like that. Thank you, whoever said that. Great job. Great job. Now, what if it was like this? Square root of b squared minus 4ac, all of it squared. Then you could cancel that out. But you cannot cancel out an individual piece of a polynomial that happens to be a square just because it's in a square root. Okay? How about E? What would E be, gentlemen? Yeah, that's going to be -3, and there's no worries there because it's an odd root. How about F? Yeah, you can't really do that. Okay? All right. Now, this gets a little tricky, so I need you to pay attention. Whenever I have the nth root of n, we just learned that we cancel out the radical with the power, and that's great. However, if it's odd, we don't care. It's just the answer A. But if n is even, you got to put it in an absolute value. What am I saying in English words? In other words, when you take out an odd exponent from an even root, it must be an absolute value. Why, Moro? Because that variable could very well be a negative. For example, if I have the square root of x to the 4th power, okay? This is a square root, right? Invisible 2. Do you guys remember this is a while ago, how do we simplify variables inside of the radical? Good. You divide by the index. How many times does 2 go into 4, guys? 2 times. So x squared, right? Okay, right? Okay. Nice and easy. What if there's no problem? I pulled out an even exponent from an even root. You feel me? Now, what if I just said the square root of x squared? This cancels, but now it's going to be an absolute value of x. Why? What's the power of x there? 1. Is 1 even or odd? Whenever I pull an odd exponent from an even root, I must put it in absolute value. Why, Moro? Can't this x technically be -5? If I don't have it in absolute value, then it's invalid. I have to have an absolute value. So whenever you pull a variable out of an even radical, if that exponent is odd, it must be put in absolute value. So let's simplify. Square root of 16x to the 8th. Okay. Square root of 16 is 4. That's pretty easy. How many times does 2 go into 8, guys? So that's x to the 4th. I pulled an even out of an even. We're golden. Next. Cube root of a to the 6th, b to the 9th. 6 divided by, what is it? A squared and b cubed. Beautiful. I don't have to worry about absolute values at all here because it's an odd index. The only time I have to worry about the absolute values is when I pull an odd exponent out of an even. How about here? What's the 4th root of x to the 8th? Y 12th. X squared. Absolute value of y cubed. Beautiful, son. Why, Moro? Why? Because I pulled an odd exponent out of an even root. You feel me? You feel me? I pulled an odd exponent out of an even root. Yes, sir. There was only the plus or minus is only activated, like we've talked about before, when you solve an equation, or if I put for you in front here, I want both roots, plus or minus. If I don't put a plus or minus in front, then they just want the principal positive root. When you're using this to solve equations, though, you do need a plus or minus for even roots. Yes, sir? You do not put the 3 outside of the absolute value. It will be wrong. It's y cubed. That whole thing has to be in an absolute value. How come? Because what if y was -1? -1 cubed is still -1. I got to contain that in absolute value. If I put -1 and then I cubed -1, it'd still be -1. So I have to have the whole thing contain an absolute value, sir. It's a great question. Thank you. You have a question, my brother? Okay, how about this bad boy? D. Okay, this is first of all, this negative, anytime you have a cube root and you see a negative, go ahead and make your life easy. Pull out a negative. So that's just a negative right there. Done. That's gone. It's not an I because it's an odd index. But whenever you have an odd index with a negative, pull out that negative immediately. Now, what's the cube root of 2/3 to the 6th power? 2/3 squared, right? Which is 4/9. Do I have to put that in absolute value? No, no. First of all, it's an odd root, so I don't care. It can be positive or negative. It does not matter to me. The only time I got to worry about that absolute value stuff is with even roots. A to the 12th, that's going to be A to the 4th, and then B to the 5th. Ding dong, the witch is gone. Good job. Next, what's the square root of 81x to the 4th? 9x squared. No need for absolute values because the power of 2, x has a power of 2, which is even. How about this bad boy here? Yes. Nicely done, boys. Well done. That's absolute value of x cubed times y to the 4th. For any of those last stragglers that are still like, dude, I know you're trying hard, Moro, but what the heck did you just do? I pulled an odd exponent out of an even root. So it must go in absolute value. Does that make sense? Okay. Now, you can write radical expressions in an equivalent form using fractional or rational exponents instead of a radical sign, guys. This is very important. In general, the nth root of x, please remember that this x has an invisible little 1 as an exponent, right? So when I have the nth root of x, or the nth root of any value, x can be any real number, I'm going to write this as x to the 1 over n. Basically, it's x to the power over the index. So I'm taking the power, the exponent inside of the radical, that's my numerator, and I'm taking the index, that's my denominator. Okay? This is just another way to rewrite the radicals. Correct, sir. Same exact procedures. I don't like working with rational exponents. Whenever I see rational exponents, and I know this, I don't like it though. So I'm going to convert back to a radical. But you got to know how to do that. So, how does it work? Square root of 36, this is 36 to the 1/2. Cube root of 64, this is 64 to the 1/3. Fourth root of 16, this is 16 to the 1/4. It's literally that easy. You got to know how to go back and forth. You got to know how to toggle between the two. Now, for rational exponents, that was the general form, but you know that I like to be complete. So you got to know how to go from one to the other backwards and forwards. So when I have x to the 1 over n, that's the nth root of x to the 1 power. If I have x to the m over n, assuming that m is something other than 1, that's going to be the nth root of x to the m power. Remember, this numerator is the exponent inside of the radicand. This denominator is the index. Now, you could also have done this form, which is the nth root of x, but all of it raised to the m power. Why? What happens when you raise a power to a power? What do you do with those exponents, guys? You multiply them. Very good. If I have x to the negative m over n, that's going to equal 1 over x to the mn. Remember that when I have a negative exponent, I just bring that sucker down, which then will equal 1 over the nth root of x to the m power. These are all very important laws that you must know how to use, my brothers. Now, let's convert. You are on the right track. You just said it incorrect. I'm going to help you with that. This would be the 7th. Whoa, sorry about that, guys. Little malfunction there. This would be, for sure, 7th root of x cubed. I know you know what you were saying, but you don't say 7th radical, you say 7th root. Thank you, my brother. Great job. What about this? We'll start with 1 over y to the 3/5, 0.5, but that's 1 over y to the 3 1/2, which is 1 over y to the 7/2, which equals 1 over the square root of y to the 7th. Okay, I heard someone very frustrated. Why was this frustrating? Talk to me, sir.
I got lost. I got 1 to the radical twice 7. I got the 7 part, but then you lost.
Okay, thank you, my brother. Remember that this numerator is the exponent of the radicand, and the denominator is the index. Thank you, sir. How about w to the negative, bless you, 5/8? 1 over w to the 5/8, which equals 1 over 8th root of w to the 5th. How about w to the 0.2? What is 0.2 as a fraction? 1/5. So this is w to the 1/5, which equals the 5th root of w. It's not that bad. Does it look a little foreign and strange? Sure, of course it does. But everything is strange and different at first until you learn it. But I know you guys are going to practice this and you're going to learn it. Just a little reminder. I'm not going to go over it again, but it's just another little reminder. Oh, I already did it. I did some of these here for you. Sorry about that. All right. Now I want to convert this into exponential form. Okay? Exponential form. This is going to be a to the 5/2. The exponent in the radicand is the numerator. The index is the denominator. What would b be? Y to the 4/5. Very good, my brothers. Very good. What about c? What would that be? This is x to the 3/4. And you know what? I don't like the way I wrote that. Make sure that it's up at the top. X to the 3/4. How about d? B to the 3/5. Very good. It's not bad once you understand the mechanics of it. It's very easy. Thank you, my brother. Okay. What is each number in simplest form? Okay, let's do this. This is 1 over 16 to the 5/2. Because that's what 2.5 is. Which equals 1 over the square root of 16 to the 5th power. Now, I want everyone to chill for a second. And don't worry, I know you're looking at the clock, you're looking at what we have left. We're not going to finish today, and that's fine. But just pay attention to this one thing, and I'll leave you with this. I want this to be as easy as possible. Whenever you see something complicated like this, some people say, oh, I'll go to the calculator. I will do this in my head any day of the week quicker than a calculator. and I'm going to show you how. What's the square root of 16, guys? Now, what's 4 to the 5th power? 256. Because 4 times 4 is 16, times 4 is 64. Oh, actually, no, I'm wrong. It's 1012. 1012. Because 4 times 4 is 16, times 4 is 64, times 4 is 256, times 4 will be, actually, 1024. Wow, off. Boo. All right, listen. We're going to end right here. We still have the rest of this page and one more, which we will do on Monday. All I'm asking is for you to really understand everything up to this example, because the first thing I'm going to do on Monday is I'm going to give you a quiz on this first part. Thank you. God bless you. Have a great day. Hope you learned a lot.